Question 7. First part. The equation of the estimated least squares regression line of y on x for a set of bivariate data is, hold on, where's my cursor gone? Is y equals to a plus bx. Right? Explain what do you understand by the least squares regression line of y on x. So suppose we had this bivariate data, right? So I don't, no, sorry, that's not quite as neat as I'd hoped it would be. I've got this bivariate data that's just, you know, randomly, not random of course, so there's some pattern to it, and so it's there, and there's a certain amount of random noise. And I have my least squares regression line, which may look something like this, right? Well, what does this do? What this does, if this is the line y on x, right? What this does is it minimizes my vertical errors. So if we call this E1, and this is E2, this is E3, this is E4, this distance in here is E5, this distance here is E6, right? It would actually, the line y equals to a plus bx minimizes the sum of the squares of the errors. So the sum from I equals 1 to 6 of ei squared. So that is, if you added these up, or took each of these and squared them and then added them up, this line has the smallest one of those values. Any other line will increase that error term somehow. Now there's a couple of interesting things to note here. The first is, if this is what the line of y on x does, well, what about the line x on y? So if I had the line x on y, and let me just put some points up here for the sake of it, the line x on y is going to minimize the horizontal errors. So this would be my E5. This would be my E4. This would be my E3, E2, and E1. So for the line x on y, the line x equals to a prime plus b prime y minimizes the sum of the squares of the horizontal errors. So that's why we have x on y and y on x. It depends what we want to minimize, whether the error is in the vertical component or whether the error is in the horizontal component. And this is why, if x is the controlled variable, so we can control it very precisely and the error in x is small, then the error is more likely to be in y. So that's the one that needs minimizing more. So if x is the controlled variable, I always use the line y on x, because there's no error or negligible error in x that I need to worry about. Now, the other thing that I need to ask, or I should ask, is why does it why does it minimize the sum of these squares? Why do I need to square all these terms? Well, the simple answer is because this term E2, for instance, where the data point is below the line, this would come out as a negative distance, right? And so in order to make that positive again, we square it. Now, I hear you thinking, if we just needed to make it positive again, couldn't we just take absolute value? To which the answer is yes, but that's kind of difficult. And in fact, if you take the absolute value, it means that you have a lot of trouble when it comes to differentiating this function to minimize it. So this least squares line actually comes from a lot of differentiation that we don't see and we don't make use of, but it is there. And that's why we use squared, because we can differentiate a square very easily, but we can't differentiate an absolute value with as much ease. So this is the answer to 7 part 1. It is the line, y on x is the line, means that the line y equals to a plus bx minimizes the sum of the vertical error, the sum of the square of the vertical errors, and that's why it's called the least squares regression line.